Hello. Um, so today we'll be continuing with the lecture that we started about IP protocols and IP addressing. So before we actually took quite a long break, we were able to finish the discussion with regards to the differences and the characteristics of both TCP and IP. Okay? Then we were able to differentiate and share the similarities between the OSI layers and the TCP IP layers. We put a bit of context into Internet Protocol, the differences between IP version 4 and IP version 6. We've already discussed information required to identify computers on the TCP/IP network, such as the MAC address, composed of the OUI and the vendor assigned, and of course the IP address, which could be a public IP address, further subdivided into a static public address or a dynamic public IP address, or a private IP address inside a network used by the computer to talk to the router. We've mentioned the different classes of IP addresses and their ranges, how to be able to identify them. We've also mentioned the parts of an IP address, which is the network ID field and the host ID. Then we determined the function of the subnet masks. This is used by our devices to be able to separate the host ID from the network ID for the IP address. Now, depending on the class of IP address, it uses a different subnet masks. So shown here, we have the one for class A, class B, and class C. We defined what the default gateway is, and we learned how to, or we reviewed how to convert binary to decimal and vice versa, as this is needed to be able to determine IP addresses both in the dotted decimal and the dotted binary format. Although we're usually used to as future system administrators or network administrators, we will be mostly looking at the dotted IP or dotted decimal IP address, but our devices can only understand the dotted binary address. So it is a must, or still a must, for us to be able to know how to convert between the two. And of course, this is a basic knowledge for all IT students. We're able to classify the classes of IP addresses and how to be able to identify them. Now, for the public, we use the class A, B, and C. For multicasting, we use class D. And for experimental and research purposes, we use class E. With that out of the way, we will be focusing our attention to the next part of our topic, the supposed next part of our topic, which is the subnet mask or subnet masking and how it works. As mentioned a while ago, we use the subnet masks to be able to differentiate to differentiate the host address and the host ID and the network ID. Now, as persons, we could actually just memorize class A, B, and C and be able to determine what part is the host ID and what part is the network ID. But of course, that is not how the devices work. Our electronic devices, in order to separate the two, would be using a subnet masks dependent on the class of IP address. So I'll be showing today how the process of subnet masking works and how it applies to determining the host ID and the network ID. So for example, we have the IP address 200.133.175.33. So this would be our IP address. Okay? Now, we already know, because this is in the 200 range, we would know that this is part of class C, as class C is any IP address starting with 192 ending to 223. So we already know which part is the network address or the network ID and which part is the host ID. So the first three octets are the network ID and the last octet would be the host ID. Now, what we want to do is to be able to separate our network ID with the host ID. With that, we will be needing our subnet masks. So going back from our previous discussion, as mentioned, that the default mask for class C is 3 straight octets or 3 straight 8 or groups of 8 of ones. And the last octet are all zeros. Shorthand /24 to denote the number of ones in the subnet masks or the default masks. So we will be using this because we already know, or we were already able to determine that this is class C. So we'll use that default mask /24 to be able to separate the network from the host ID. So we need to convert our IP address first into its binary equivalent. So in this case, that would be this value here. Okay. So let's have a review first of how we convert this in case you forgot already. So what we're going to use would be, I've already taught you several ways to do this, but the primary two ways would be continuous subtraction or continuous division. Okay. So let's use continuous subtraction first. Okay. So we have 200. So what we do is we think of a power of 2, the largest power of 2 that we could use as a subtrahend for our IP address or for the first octet, which is 200. So powers of 2, that would be 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, then 256. So the largest one without going over would be 128. Let me just write something at the bottom. So we have your, let's write the powers of 2 here. No, not 356. 256. 128. 64. 32. 16. 8. 4. 2. 1. Okay. So this represents our 3 octets. So we're able to subtract 128 with 200. That would give us around 72. Okay. Because we were able to subtract 128, so we were not able to subtract 256. So we mark it as 0. We were able to subtract 128. We put 1. Now, let's check if we can subtract 64. Yes, we can. Okay. So, which gives us 8. Okay. So we were able to subtract 64. So we put a 1 on it. Because 8 is remaining, we won't be able to subtract 32, 16, and the only thing we can subtract would now be 8. So we do the continuous subtraction until we get a difference of 0. So the last subtraction that we did created a difference of 0. That would mean that all other answers would now be 0. So that means the converted binary equivalent of 200 would be 0110 01000. Um, just some correction. 1 to 8 would be the largest number in the octet because, yeah, octet means 8. So the highest possible would be 1 to 8. I have to 256 would not be possible because the highest possible number in an IP address dotted decimal would be 255. So let me just correct that. So that means this would be our converted IP address. So 11001000. So that is what we have here. So if we follow the same procedure for 133, 175, and 33, we'll be able to get this equivalent binary IP addresses, which is the one shown here. Okay? Then we apply a default masks at the bottom, which is composed of 24 ones and then zeros at the end. Now, what we do is we pair each of the numbers and we do an AND logic function between the IP address and the default masks per bit. So, to give you an idea, the AND, the logic function AND, would result in a value of 1 if and only if both of the values or the input is 1. Else, it would be 0. Another way of describing this is if one of the inputs is 0, the output would be automatically 0. The only way it would be 1 is if it is equal to 1. Now, what would happen is that because all of these are 1, if you look at our input here, if the second output is 1, it would just have the same output as the initial input. So a 0 ANDed with 1 is still 0. 1 ANDed with 1 is still 1. What I'm trying to say is using 1 would mean retaining the number. But if we look at the first and the third part, ANDing anything with 0 or using the logic function AND 0 with any binary digit would automatically result in a 0. So you use 0 in the AND logic function to reset the values of the bit to 0. In order to retain them, we use 1. And that is what happened here. Because the first 24 bits of the default mask are all ones. The first 3 octets were retained from the IP address. Now the last default masks were all zeros. So that means whatever it is in the last octet of the IP address, it would turn to 0. So the result would be when we AND 200.133.175.33 with its default mask for class C, it would result in the same first 3 octets but without the last octet, thereby only retaining the network portion and resetting the host portion. So that is how subnet mask works. Now, next part would be about subnetting. So there are times that we were assigned an IP address. Normally, when we have an IP address, we could build a single network for a single IP address assigned to us. Now, if you want to subdivide or to connect multiple networks or subnetworks with a single IP address, we use what we call subnetting. So, as mentioned here in your handout, subnetting is the process of borrowing the host ID field or a bits from the host ID field to a new subnet ID field. So what that means is that from the network ID and the host ID, we now get a third ID, which is the subnet ID. The subnet ID would come from the host ID, not the network portion or the network ID. We cannot change the network ID as that is the one assigned to us, but we can work around with the host ID. So in order to do subnetting or create subnetworks within a single IP address, we use the subnetting portion or we use subnetting and borrow bits from the host ID. So let's have a walkthrough using an example here. So let's say a company is granted a site address of 138.45.0.0 and the company needs 45 individual networks or subnetworks. Again, normally without subnetting, we can only create a single network with this IP address. But with the power of subnetting, borrowing from the host ID, we could actually create individual subnetworks. By the way, 138 from our discussion is part of class B, which means that the first two is the network ID. The first two octets, 138 and 45, is the network ID rather, and the last two are the network ID. And that is where we will borrow bits from to create a subnetwork. Now, that would be step one. We need to determine the class and the default mask of the IP address. Because this is again class B, we will be converting it to binary later. And class B has its first two octets as a default mask, which is /16 of straight ones, and then the zeros will represent the host ID or would reset the host ID. Now it was mentioned that we would be needing 45 individual networks. So what we're going to do with this knowledge, because we need 45 subnetworks, we need to be able to determine how many bits from the host ID we would need in order to cover the 45 individual networks. We cannot just get bits just to satisfy the 45. We need to make sure that we will be able to efficiently cover all 45. And that would only work if the IP address is already in binary. So, how do we know or how do we determine the number of bits? We convert 45 into binary and we will check how many bits are needed to show or to give the 45 or the conversion of the 45 decimal to binary. So going back here, let me just delete this. So we have 45. So with the powers of 2, the first one, the largest bit without going over is 32. Okay. Technically, we already know with just this knowledge how many bits are needed, because 32 would be the largest power of 2 without going over 45. That means we will be needing 1, 2, 3, 4, 5, 6 bits. But let's continue our conversion. So minus 32, this would be equal to 13. So this would be 1. We cannot subtract 16. The next largest one would be 8. And then we have 5. So we put a 1 here because it's possible. We're able to subtract 1. Then 5, the next largest possible would be 4. So we're able to subtract 4. Then we have an answer of 1. We won't be able to subtract 2, but we'll be able to subtract 1. Again, we end once the difference is equal to 0. So the converted binary number of 45 would be 101, 101, which means that we will be needing 6 bits. So we'll be borrowing 6 bits in order to adequately cover the 45 subnetworks we'll be needing. Okay? So in this handout, the solution or the conversion technique that was done was the continuous division, which would also result in 101,101, which is 6 bits. But how many bits do we have for the host ID? Again, the first 2 octets would be the network ID, that would be 16. That would mean we would have 2 octets, the third and fourth octet for the host ID, which is a total of 16. So once we determined that we needed 6 bits, okay, we would be creating our subnet ID. Okay. So we have our default mask here, and we would be adding 6 bits of 1s in our default mask to create a custom subnet mask. Remember, we would be borrowing 6 bits as part of our subnet ID, and that is this what 6 1s is for. So once we use this custom subnet masks, we'll be left with the network ID and our subnet ID. Now, when we have our custom subnet masks in place, if we look at the 6th bit here, because we need to determine the custom subnet ID of each of the networks. So we have the network IDs here, the 2 octets, and then we have the borrowed 6 bits here. So we'll be using the last bit on the right, which is actually found when we look at the powers of 2, it's found on the 4th position in place value of binary. So that means the subnet mask or the subnetwork would be identified with an incrementing or increasing value of 4. So for example, our original network ID without subnetting is 138.45.0.0. But with subnetting, the first subnetwork would have 138.45.4. Then we increment by 4 again. So we have 8. Then we have 12, 16. So there is an increment of values of 4. Now, this would ensure that we will be able to cover 45 subnets, but it would actually go over 45. We'll have around a maximum of 62 subnet masks. Now, we can't use 252 as it is not a valid subnetwork address. Okay, so this is what we do to list all of the subnetworks. Now, in order to determine the number of subnets without listing every single one of them, we use this formula. So 2 raised to n, or in this case s, minus 2. S or n being the number of bits borrowed for the subnetwork ID. In this case, 6. So 2 raised to 6 would be 64 minus 2, which would be 62. So there's an error here. There should have been 2. Why minus 2? We can't use the first one as a subnetwork, the 0.0.0, because that's the original network ID and not valid for use as a subnetwork address. And the last one, the last portion, is not also a valid subnetwork ID. Okay? So we can actually get or cover up to 62 subnetworks, which is 17 more than what we needed. Okay? Now, the next question would be, how many hosts could each subnetwork use? Remember, we actually borrowed 6 bits from the host ID. So that means the 6 here cannot be used as part of the host ID. We could use the remaining 10. So how do we determine the number of networks? It's equal to 2 raised to n, in this case h minus 2, h or n being the number of bits for the host ID. In this case, 10. So 2 raised to 10 would be 1024 minus 2, which is 1022 total hosts. Why is there minus 2? Because we can't use all zeros and all ones. So anything in between is fair game or usable. Okay? So that is the process of determining the subnetwork ID. Hopefully you learn a lot from this specific lesson. The next video lecture, I will be giving more examples or additional examples for subnetting and determining the, I don't know if I'll be giving something for subnet masking, but most probably I'll be giving one for subnetting. Subnet masking is like a portion already of subnetting. When we try to separate the host ID from the subnet ID and the network ID. Anyway, thank you very much for listening. Hopefully you learned a lot. And if you have any questions, don't hesitate to put in your comments. If you found any errors with my lecture and discussion, please feel free to correct me. I'm open to corrections and to be able to make sure that knowledge that we produce is accurate. Thank you very much and good day.